Welcome back everyone to this series on index notation and Einstein Summation Convention. In this episode, I'll cover problems 2 and 3 of the worksheet that we did in the last video. If you haven't seen it yet, I invite you to go watch it. And we covered every problem except for, well, every question except for question 7 of problem 1, which I'm going to do right now. But first, let's revise some index notation relating to matrices. So given AB equal to C, where A and B are matrices with dimensions m by n and n by l respectively, we want to find the entries C sub I, j. Now, the first index here denotes the row and the second one the column. So here, I will have range 1 all the way to m, and j will have range 1 all the way to l, because that's the dimension of C. Okay, well this is equal to the entry of the ijth entry of AB, and the rule to describe this in terms of just the entries of A and B is given by this. The sum as k goes from 0 to n of AI, k, bk, j. But of course, using Einstein Summation Convention, we're going to suppress the summation and we'll just write aik, bk, j. Okay, but what about if we had 3 matrices multiplying? Well, it's an easy extension of this. So if we have ABC is equal to D, that tells us that D sub ij, or the ijth entry of D, which is in the ith row and jth column, is equal to the ijth entry of ABC. Now, you can apply this rule twice. So maybe you can apply it on A times BC, or you can just do it quickly like this. AIK, BK, H, CHJ. And here we can see that the indices that are summed over are repeated exactly once, or twice, I guess. And we do indeed have I and j once on both sides. This brings me to my next point. When we have an index which appears only once, we call it a free index. If it is repeated, we call it a dummy index. Which is a bit mean, but that's the convention. Okay, and now we're going to go on to problem 1.7 as I promised. As before, you can find this problem set in the description, and let's get going. So the question says, given this transformation rule for B and C, I haven't written it, but it's the same for C, where the vector B under an orthogonal transformation, which in other words means we multiply the vector B by a rotation matrix R. Now this matrix is orthogonal, so that means that if we multiply itself by its transpose, that returns the identity. In index notation, this is very important, the ijth component of the transpose is the jith component of itself. This is because this index refers to the row and this index refers to the column, but if we transpose a matrix, we switch those, which is why these indices get switched. And if we apply the index notation that I showed you in the last clip to this identity, we'll find that r sub ij, r sub kj is equal to the identity's ikth entry, but that's only equal to 1 if it's the diagonal entry, and it's equal to 0 otherwise. We can write that as a Kronecker delta. And this is a reminder of an identity that we're going to use in solving this problem. Okay, so we're given this transformation rule, and we're asked to find how A, which is defined as B cross C, transforms. Okay, let's write the ith entry of A. That should be a piece of cake by now. That's just the definition of the cross product in index notation. This is going to transform to, I'm going to call it AI or A tilde, the ith component of A tilde, epsilon ijk, B tilde j, and C tilde k. But we know what these are, given the transformation rules, so let's write it here. So it'll be Rj something, B something. And I'm going to call that alpha. Remember, this is a dummy index, so it's summed over, so you can call it whatever you want. Here, the only free index on the left-hand side is I. In fact, it's the only index. So then the only free index on the right-hand side should also be I. And that's the case so far. C tilde, I'll do a similar thing, where I'm going to call it this dummy index beta instead. Okay? And now I'm going to split this sum. I'm going to write it as half itself plus half itself. But for the second copy, I'm going to switch alpha and beta here. So we're going to have b sub beta and c sub alpha. And I'm also going to switch j and k. Now, what that'll do is that'll keep rj alpha and rk beta, but it'll introduce a minus sign because I've switched j and k. And as you remember, if we go one permutation away from an epsilon symbol, that'll give us minus that epsilon symbol. So that'll give us minus the same term, but instead of b sub alpha c sub beta, it'll be b sub beta c sub alpha. Okay, why is this useful? Well, we're going to use this identity to write this as delta alpha A delta beta B minus delta alpha B delta beta A times B sub A C sub B. Now here I'm summing over A because it's repeated, and this term will only be non-zero when A is equal to, this term will only be non-zero when A is equal to alpha, so we're going to get B alpha, and similarly when B is equal to beta, so we're going to C beta. But here's the other way around. Okay, so as we saw last time, this difference of Kronecker deltas is actually the product of two Levi-Civita symbols. So let's write that. K beta. I'm having trouble reading my own handwriting. This is equal to, so here we have alpha is playing the role of j and A the role of n. So we're going to have epsilon. The first index is repeated, so I can call it whatever I want. I'm going to call it gamma. So it'll be alpha, beta, epsilon, gamma, AB. If you don't understand how I got from here to here, I invite you to apply this identity to this, and you'll see that these are actually the exact same thing. Okay? But notice, I've just written A in a different form, right? The old A, not A tilde. So I can rewrite that then. As epsilon gamma alpha beta A gamma. Okay. And we're asked to show that this is actually equal to, this is what we're going to find out, the determinant of R being the orthogonal matrix which is applying this transformation, times Ri, we'll call it, for example, J, Aj, where A is the old vector. Okay. To do this, I'm going to define the determinant in index notation, and then we're going to see if we can massage this into this form. Okay, so in the last board we found this, and we're told that the answer should look like this. So what I'm going to do is, I'm going to see if we can show this equality, which if you look closely, that's what we're trying to show. Because if the left-hand side is equal to the right-hand side, then we know that AI tilde will be equal to the left-hand side, which is Ri gamma delta R, times A gamma, which is exactly what we're trying to show. Okay. Now, how do we do this? I think you can go about it a few different ways, but what I'm going to do is I'm going to show that this equality is true by transforming it into other equalities that are easier to prove. Okay. So the first thing I'm going to do is I'm going to multiply both sides by Ri gamma prime. Gamma prime is a different index to gamma. Okay. Is equal to 1/2 J epsilon gamma alpha beta Rj alpha Rk beta Ri gamma prime. Okay. But now we know what this is based on R being orthogonal. This is just delta gamma gamma prime. Delta R. Determinant of R, sorry. Okay. Is equal to the right-hand side. So this tells us that this equality is true if, when gamma is equal to gamma prime, the determinant of R is equal to this, and when gamma is not equal to gamma prime, the determinant, or this is equal to 0. Because if gamma is not equal to gamma prime, then the left-hand side just vanishes, because this is 0 times just some number. And that would mean that the right-hand side should also vanish. Okay. Well, first, let's see what the determinant of R looks like in index notation. So this is supposing gamma is equal to gamma prime. The first case, okay. Well, if gamma is equal to gamma prime, then this side turns into delta gamma gamma, but as I discussed in the last video, that's not equal to 1, that's equal to 3. So 3 determinant of R is equal to the right-hand side where we're saying gamma is equal to gamma prime. So a half epsilon ijk epsilon gamma alpha beta Ri gamma Rj alpha Rk beta. If you divide across by 3, that gives us the determinant of R is equal to 1 over 6 times all of this, which if you look up the definition of the determinant in index notation, is indeed the definition of the determinant in index notation. So we've actually found that this equality holds when gamma is equal to gamma prime. Now we just have to show that it also holds when gamma is not equal to gamma prime. Okay, so just to reiterate, if we show that this equality is true, now this equality is delta gamma gamma prime, determinant of R, then that must mean that this equality is true. But if this equality is true, then we've proven what we want to show. Okay. So we've already done the case where gamma is equal to gamma prime. Now let's do the case when gamma is different from gamma prime. So here, this will vanish, which should give us 0 is equal to 1/2 epsilon ijk epsilon gamma alpha beta Rj alpha Rk beta Ri gamma prime, where here gamma and gamma prime are definitely not the same. So let's suppose gamma was equal to 1. Here, you could choose any number from 1 to 3, but I'm going to choose 1 to show that this is indeed equal to 0. If gamma is equal to 1, the only non-zero terms in this sum, which I'll remind you has no free indices, right, other than gamma and gamma prime. So it's summed over I, j, k, and alpha and beta. The only non-zero terms in this sum will be when I and j and k are all different, and gamma and alpha and beta are all different by the definition of the Levi-Civita symbol. Okay. So if gamma and alpha and beta are all different, and gamma is equal to 1, then I can just choose alpha and beta to be, for example, 2 and 3. It doesn't matter which order you choose, but this is just to demonstrate. So that means, let's say alpha is equal to 2, and that actually fixes beta to 3. So, for example, this will give us 1/2 times epsilon ijk. I haven't defined I, j, or k in any way yet. Epsilon, well, I said 1, 2, and 3, right? 1, 2, 3, Rj 2, Rk 3, and here we have to have gamma prime being different to gamma. So that means I can choose gamma prime being either 2 or 3. I'm just going to pick 2. It doesn't matter. Ri2. Okay. Now the next step, I'm going to ignore the symbol for the moment, and I'm going to switch I and j in the Levi-Civita symbol. And if you remember what I told you earlier, when we do one permutation of the arrangement of the indices, that gives us minus what we had originally for the Levi-Civita symbol. So that's 1/2, or minus 1/2 epsilon j I k. I'll write the rest. 1, 2, 3. R j2, R k3, R I2. So here, I've switched I and j in the Levi-Civita symbol. But notice, I can just rename ij and ji, since they're dummy indices. So I can do that if I want, and you can too at home. So this will give you minus a half, epsilon ijk. Here, I'm not switching the order of the indices. I'm actually just renaming. 3 ri2 rk3 rj2. But notice, we found that this line, which is just any non-zero term from this, we're supposing, is actually equal to minus itself. Here, all we have to change is the order of multiplication, but these are just numbers, you can do that. Which tells us if this line is equal to minus itself, then it must be equal to 0 whenever this is true. But whenever this is true is whenever this could not be 0 in the first place. So that means it's always 0. So we've shown that when gamma is not equal to gamma prime, this vanishes. So we've shown that this equality is true, which in turn shows that this equality is true, because this comes from this. And if this equality is true, then we've shown what we wanted to prove. And that is problem 1.7, a very hard problem. So if you got it yourself, congratulations. Okay, so now we're going to move on to problem 2.1, which asks us to identify the entries in the circle row with the objects in the square row. Okay, our strategy to do this will be to find the components of each of these objects and try and match them with any of the ones in the circle row. Okay, let's start with the first one. So mv is a vector, so let's take the ith component of that vector. That's defined as mij vj. To see this, I'm going to write them out as you probably saw them in the linear algebra class, and I'm going to see if this makes sense. Okay. M is an n by n matrix, and V is an n-dimensional vector, column vector. So that tells us that we're going to have M11 all the way until M1n in the first row. This is 1n, by the way. And then this is going to go all the way down to Mn1 to Mnn. Okay, and this is multiplying V1 all the way to Vn. Okay, what's this equal to? Well, we were taught that you multiply the first row by the first column, and that'll give you your first entry. And then you multiply the second row by the first column, and that'll give you your third entry in the row, or in the column, sorry, etc. Here we only have one column, so we're only ever going to have one column resulting, which is expected since we're multiplying a vector by a matrix, we should always get a vector. Okay. Here, we have M11 times V1 plus the second term in this row will be M12 times V2 all the way until M1n times Vn. And this will go all the way down until we get Mn1 times V1 plus Mn2 times V2 plus all the way until Mnn times Vn. So we can see if we take the ith component of this, or we take the ith row, then we're going to end up with this being I, the first index of M being I, and the second index of M and the index of V are being summed over. So here 1, 1, 2, 2, all the way until Nn. And that indeed is represented by this, this term here. Okay, do we see this anywhere? We do. So this one corresponds to this one. Okay, now we're going to do the same thing for V transpose M. V transpose is a row vector this time. Okay, so it's going to be V1 all the way until Vn, multiplying M. I'm not going to write it out explicitly. But if you apply the same rule for matrix multiplication, row times column, and then row times column until you do everything, this will give us just another transpose vector, which will look like this. V1 times, so it'll be the first row times the first column. So it'll be V1 times M11 plus V2 times M21 all the way until we get to Vn times n sub, or m sub n1. And that'll be the first entry of this n-dimensional row vector. The second entry will be this row times the second column. And then the nth entry will be this row times the nth column of n. Okay, but in general, if we take the ith component, So if we take v t m sub I, that'll give us the ith component, which we just said is going to be the row times the ith column of m, but we can write that as v sub j m mji. Okay. Now here, j is a dummy index that's summed over, and I is a free index. Do we see this term anywhere here? Not exactly, but we do have the same structure, where the first index of m is repeated with the index of v, and then we have a free index left over. So this is indeed equal to v transpose m in index notation. This would be the jth entry of v transpose m. Okay. And before we move on to the next parts, I want to remind you what the trace of a matrix is. The trace of a matrix, so let's take some matrix A. So it has to be a square matrix, by the way. The trace is the sum of the diagonal entries. Okay. So we could write that if we wanted, the sum of the diagonal entries. So this will be from I to n, if it's an n by n matrix, of A sub, well, if it's a diagonal entry, it'll just be the index repeated, right? But once again, we can suppress this summation with Einstein Summation Convention, and that'll just give us A sub II. Okay, so the trace of A is A sub II. Okay, so the trace of any of these matrices then will be, or these two traces, will be a lot easier to compute now. So let's start with this one, trace of m squared. We're trying to find, using this rule, the trace of m squared. So we should probably find the ith component of m squared. Well, m squared is just equal to m times m, right? But we saw how to find the components of this. If we were trying to find the ijth component of m squared, that would be mik mkj, or summing over k. Okay. So if we're trying to find the ijth entry. If we're trying to find the ith component, or entry, then that'll just be mik mki. Okay. Do we see that anywhere? No, we don't. So this is in fact not written on the board anywhere in the circle row. Okay, what about the trace of MM transpose? Well, MM transpose has entries right here. MN transpose, the ijth entry of this is equal to MIK M transpose KJ. But I already told you what the kjth entry of the M transpose would be. We just switch the indices. That'll give us MIK M JK, which tells us that the ith component of this is equal to, instead of J we write I, so that'll be MIK MIK. Is this anywhere on the board? Yes, it is, where I is the same, but K has been replaced with J, another dummy index. So we've seen that this trace can be written in this form. Okay. And I think these three you can do as an exercise and see which ones correspond to which. They're not too hard. And in fact, if you use the fact that AB transpose is equal to B transpose A transpose, you can only do one of these two and you'll get the same answer. Problem 2.2 I will leave to you as homework. I think you can do it with all the knowledge I just taught you. And if you don't know how to do something and you really want to know for some reason, ask us a question in the comment and we'll try to get around and answer them. Okay, before we start problem 3, I want to give you some motivation as to why this is important. So if you're doing a course in classical mechanics, or you're just interested in learning about classical mechanics yourself, then you should be aware that there's this thing called the Lagrangian, okay? And it's a function of the generalized coordinates, qi. If you're worried about why I is in superscript instead of a subscript, it doesn't really matter in 3 dimensions, it doesn't really matter in Euclidean space. And for consistency with the worksheet, I'm just going to leave them as upper indices. But you could easily write these as lower indices, and for the purposes of this video, it's the same, okay? Please remember that. It doesn't matter. for this video. Okay, so we have this Lagrangian, which is a function of the generalized coordinates and their time derivatives. That's what the little dot means on top, and possibly of time as well. And to find the equations of motion, we apply the Euler-Lagrange equations, which are also in terms of these generalized coordinates. Okay, and here the index I can take values 1 up to s, which is the dimension of the system we're working in. Let's start with an easy example, which is the time-independent Lagrangian for, well, it's s distinct harmonic oscillators, right? For each I, we have the kinetic energy term, which is that of a free particle, and then of mass m, and then we have s different oscillators, each with their different force constant. Okay, these are all i's, by the way. Now, how do we find the Euler-Lagrange equations for this? You might think naively that we just do delta L, delta Qi. Now, if we read this off from here, what would we find? Well, we find that here there's no Qi's, because Q and Q dot must be independent. And here, well, there's 1, and we're left over with Ki and another Qi. So it'll be minus a half K sub I, like this. But this is completely wrong, because we've used a free index here. Well, for this free index, we've used what is already being summed over, or a dummy index, and we can't do that. That is not allowed. What we should do instead is, so don't do this, no. What we should do instead is take the derivative with respect to a different index. It doesn't matter whether you choose this to be I or this to be I, they just have to be different, okay? You have to be consistent. So let's say del L del Q I, and to do that, I'm going to now write this as we discussed, this will never have any Q involvement, so we can just ignore it, as the partial derivative with respect to Qi of minus a half Kj Qj Qj. I should have mentioned that here I and I are summed over, which means this is really a sum over all of the different Lagrangians. Okay, that doesn't really matter. But here J is summed over, I is a free index, and problem 3 will help you understand how we do this derivative. If you think you know how to do it, go ahead, and you'll find out pretty soon, because that's what we're doing next. Problem 3.1 asks us to compute these objects. Okay. And another one. How do we do this? So the first thing to notice is if this was, for example, x and y, and they're independent, so if we did delta x or dx dy, that would give us 0, right? Because they're independent. But what if we did delta x or dx dx? That would give us 1 because they're the same. So in general, these partial derivatives will only be 1 if I and j are the same, or we're talking about the same generalized coordinate, is another way of saying it. And there'll be 0 otherwise. But we have a name for that. That's just the Kronecker delta. So that'll be delta ij. Okay. Now, what about delta qi, delta qi? Well, that'll be delta ii by this result. And we show that that is equal to, well, in the last video, we showed it was equal to 3. That's because I could only take values up to 3. In this case, I and any of these indices we're talking about with q can take values up from 1 to s. So that means this will be equal to delta 1, 1 plus delta 2, 2 plus all the way until delta ss. So we have s copies. So that's equal to s. Okay. Now we're going to find, which is probably, this is going to be the most useful example of this whole video probably, the partial derivative with respect to qi of some matrix entry times qj qk. Okay. This matrix entry supposedly does not depend on q, so we can bring it out. It's just a constant with respect to the partial derivative. So that's m sub jk. And now we're going to apply the product rule to these. Qj delta qk delta qi. Okay. So here all I've done is I've applied the product rule of the partial derivative with respect to qi to these two terms. What does that give us? Well, the first one, using that definition up there, will give us delta ij qk. And the second term will give us qj times delta ik. Okay? Here j and k are repeated in both terms. So that means we can treat them as dummy indices, because they are. And I'm actually going to separate these two terms, and you're going to see what happens next. So if we're summing over j and we have a delta ij here, it'll only be non-zero when j is equal to I, so we can rewrite this j as an I. Mik qk. And similarly, the other one will become mji, because the sum is over k, and it's only non-zero when k is equal to I. Sorry, mji. Okay, but here k in this term and j in this term are just dummy indices. So I'm going to relabel this one as j, and so then I can factor out a qj from both. And that'll give me mij plus mji. And that's our answer. This partial derivative is equal to this. Okay, and we're going to be using that a lot, so I'll write it on the next board. Okay, so just to reiterate something I've said a few times. Here, the only free index on the left-hand side is I, right? Because j and k are both repeated, so they're summed over. And on the right-hand side, it's also I, because it's the only one that appears once. By appear once, I mean if you split it up into sums, this would turn into two separate sums. It would turn into sum over j of kji, or kj mij, plus the sum over j of kj mji. When I say the index only appears once, I mean in a term relative to a sum. Here, if you counted the number of i's, there would be two, but they're separated with a plus, which means you actually have two separate terms. And in each term, I only appears once. That's what I mean by appears only once. Here, j is repeated in both terms, so it's summed over in both terms. Okay, we're going to finish off problem 3.1, and this one seems a little bit tricky because we have an I being repeated, so we have to sum over it, and then j is the only free index. Okay, it's similar to what we just did, but you have to be a bit careful. So like what we just did, mjk is just a number, it's the entry of the matrix, we're going to bring it out as a constant with respect to the partial derivative. So mjk. And now when we apply the product rule, we have to be extra careful with the fact that the partial derivative of qi with respect to qi is not 1. We saw that it was equal to s earlier, so let's remember that. And then we have, well, I'm just going to write it quickly. Okay. So this is equal to s, because we're summing over all of the partial derivatives. So it'll be delta, or del q1, plus del q2, etc., all the way up to s. So this is s times qk plus delta ik qi. So I'm just going to choose to keep k, and I'm going to replace I with k. Qk. Okay, what's that equal to? Well, we can factor out the qk, so that gives us qk times mjk times s plus 1. As before, here the only free index is j, and here the only free index is j, which is good. Now we're going to move on to problem 3.2. In problem 3.2, we're really going to test our understanding of this, because now we have 3 k's, and m has 3 indices, but that doesn't really matter. Okay, so we're just going to do what we just did, but instead of applying the product rule to 2 terms, we're going to apply it to 3. So let's do that. It's a bit tedious, but bear with me. Okay, mjkl is a constant, so we're going to bring it out. And here we're going to do the partial derivative with respect to q, or of qj with respect to qi first, and then do the other two. Okay, so that gives us delta ij qk ql plus, now we're going to take the partial derivative of qk with respect to qi, which gives us qj times delta ik ql. And finally, we're only left with ql, and that'll give us qj qk delta il. Okay. But now we have a few deltas that we can simplify. And notice that it's the repeated index is always, it always appears once in a delta and then once in this matrix entry here. So the first one, we're going to sum over j until j is equal to I, at which point this will be non-zero. So that means we can replace this with qk, ql, mikl. Similarly, we're going to sum over k until we get k is equal to I, at which point this will become qj, ql, mjil. And then lastly, the exact same thing, but here we're summing over L. Okay. MJK. Okay, but what we have here is essentially the same term repeated twice up to a permutation of the indices. Because we have K and L being summed over, J and L being summed over, and J and K being summed over. So I'm actually going to rename K, I'm going to rename L with K and this L with J. And that'll give us QJ, QK, because I can rename a dummy index whenever I want, as long as I rename each appearance of it in the terms. Okay. Times, here I replaced J, or L with J, so it'll be M, I, K, J. Here I've replaced L with K, so I'm going to get M, J, I, K. And here I haven't replaced anything. Okay. So that's what this is equal to here. Now for the next question of 3.2, I think you can do it yourself. If you notice that I is repeated, you have to be as careful as we were last time. But the answer you get should look something like this. S plus 2 times Qj, Qk of, or times, oh no, sorry. Qj, Ql of Mj, Q, Qj, Ql times Mj, Kl. Okay. Let's notice that on the left-hand side, I is repeated, so it's a dummy index. J is repeated, so it's a dummy index. And L is repeated, so it's a dummy index. The only free index is K. And on the right-hand side, J is repeated, so it's a dummy index. L is repeated, so it's a dummy index. And the only free index is K. It's always good to do this check to see that if you haven't done anything wrong, because I almost did something wrong there by having K repeated. And you can do the same check here. The only free index should be I, right? Because we have J repeated, K repeated, and L repeated. And in the final answer, the only free index is indeed I. It's repeated once in each term. Very important. So now we'll move on to problem 3.3, which involves second order derivatives with respect to qi. Okay. So we just saw how to take first order derivatives with respect to the coordinates. Now we're going to see how to take second order partial derivatives with respect to the coordinates. Okay. This looks pretty daunting, but you can always switch the order of derivatives, or you can treat it as the derivative of the derivative. I think this is the easiest way. Okay. So the second order partial derivative of respect to QL and then or QI and then a QL of this object is equal to this. But we've already found this object here in problem 3.1. So I'm now going to substitute in our result, which was Qj times Mij plus Mji, I believe. Yep. Okay. And here, the Mij and Mji components are just constants. So here we only need to take the derivative with respect to QL of Qj, which we know is delta JL times Mji plus Mij, which is just equal to MIL plus MLI. Very nice. Okay, now for this one, we're taking the derivative with respect to Qi twice. So as before, I can write this as the first order partial derivative with respect to this object, which we found. So I'm going to write that again. Okay, this is equal to delta ij times mji plus mij, okay, which is equal to 2 copies of mii But I'm giving brownies to whoever guesses what this is. This is the trace of m. So 2 times the trace of m. Okay. And the final question, I'll let you do it, but I'll give you the answer to the final question, since you're so nice. It's 3qj, well, let me make sure. Yep, 3qj times mjim plus mij. So that's it for the worksheet. If you have any questions, leave a comment and we'll try to get to it. Thank you for watching. This has been fun. If you haven't learned anything, then I'm sorry. I did my best. If you did learn anything, give us a thumbs up and subscribe to the TPSA. I might be coming out with new videos on classical field theory and showing you the terrifying difference between upper and lower. But that's for another video. Once again, thank you. Leave a comment if you're confused.